Hello, everyone. Welcome to the Purdue Statistics Distinguished Theme Seminar Series on Deep Learning Methods and Theory. Today is the last lecture of the series, which will be given by Dr. Ruslan Salakhutdinov. Russ received his master's and PhD degrees in computer science from the University of Toronto in 2003 and 2009, respectively, and then became an assistant professor at after his PhD, Russ was a postdoctoral research associate at MIT, and then became an assistant professor at the University of Toronto. Currently, Russ is a UPMC professor of computer science in the machine learning department at Carnegie Mellon. Russ works in the field of statistical machine learning, and his research focuses on deep learning, probabilistic graphical models, and large-scale optimization. Russ has received numerous awards, including the Google Focused Award, a Microsoft Research Faculty Fellowship, and a Sloan Research Fellowship. Today, Russ will be talking about integrating domain knowledge into deep learning. To our viewers, whether you're watching on Zoom or on YouTube, you're encouraged to take your questions in the chat on either platform. We will monitor both chats and relay the questions to the speaker. Due to limited time, we may be able to only answer a subset of the questions, and we apologize if your question is omitted. At this point, let's give our full attention to Russ.
Awesome. Thank you so much. I guess everybody can hear me, right? Looks good. Okay. Let me just fix a couple of things here. So great. So today I'm going to talk about how do we incorporate domain knowledge into deep learning? And I'll sort of cover two big areas of research that's taking place in my lab. But just to highlight the impact of these machine learning and deep learning systems, when we look at the speech recognition, vision, recommender engines, language understanding, even in places like drug discovery and medical image analysis, we see a lot of work and a lot of advances. And what is it that we want to do? Well, I want to be able to build algorithms that can see and recognize objects around us, that can understand human speech, that can reason and understand natural language, that can move around autonomously, explore, plan, build strategies, and in general display human-like intelligence. Right. So that's a holy grail of building true AI systems. Now, when I think about some of the key challenges and some of the key research directions, I think that one big area of research is language understanding, and in particular, understanding and reasoning. There's been a lot of advances, and the first part of the talk, I'll focus on that aspect. The second one is we've seen a lot of advances, recent advances in reinforcement learning and control. So I'm going to show you some examples of that research as well. Another area that sort of works together with the previous ones is incorporating domain knowledge or incorporating structured prior knowledge, so that we can make our algorithms and our systems, AI systems, so that they can be more intelligent. And also there is a lot of work in the space of multimodal learning, self-supervised learning, and semi-supervised learning. So in this talk, I'll probably focus on the first 3 points. So let me jump into the first part of the talk. And a lot of this work was done by my former student, Buan Dingra, who's going to be joining Duke as a faculty a year from now. But let's look at the natural language understanding. So when we look at deep learning models, in many cases, we think about an input and an output, right? So for example, we think about, I give you an image like this, and there's a question of whether this is a cat or not, right? So think about all these, large-scale computer vision systems. Today, they're using some form of deep learning. In fact, they're using convolutional neural networks to actually make predictions. I can also build a system that does machine translation, right? I give it a sentence in English and I want a translation in French. And again, a lot of recent work in sort of neural machine translation has been done in the setting of using these deep networks. But let's say I give you the following question: which coronaviruses are known to infect people, right? And there are multiple of them. So the question is, how do you answer a question like this? And this is where domain knowledge becomes an important component of these systems. And then generally the question is, how can we use unstructured text? How can we use structured text in the form of ontologies or knowledge bases, and perhaps even tables, to get us better representation, and so that we can learn better representation and be able to answer those questions, right? So in the first part of the talk, we'll focus a little bit more on the question answering, just as a specific application area. Okay, so what are some of the key challenges? Well, the data is heterogeneous, right? So we have textual data, which is most commonly used data. You know, for example, you can look at the Wikipedia articles. The other challenge is reasoning. So we can think of it, you know, to be able to answer a question, we actually need to query and be able to extract different information from different sources of data, and maybe even, you know, understand how they related to each other so that we can answer these complex questions, right? And ultimately, we also want to do it with what's called weak supervision, where, you know, I just give you inputs and outputs. I give you, for this question, this is the answer, and for this question, this is the answer. But I don't necessarily tell you exactly, you know, where that answer can be found, how it relates to these, you know, other, you know, ontologies or knowledge bases, and so forth, right? Just because otherwise, it's a very laborious task to actually build or label these data sets. And by the way, as I go through the talk, if there are specific questions, you know, feel free to ask me those questions. Now, when I think about what's been traditionally done, and in, you know, traditionally when we look at a lot of systems, like, you know, when we look at Google, Apple's, and Microsoft's, a lot of IT companies, what they do is they build knowledge bases, and for a good reason. So let's say I go through Wikipedia articles and I extract some information which we think of these as, you know, as concepts, right? We think of them as entities. So that's the first step, is to create. And generally, you know, we would go, and the number of entities would be on the order of, you know, millions, right? So all the nouns, perhaps different names and names of places, those would represent entities. And then we would also try to extract relations, which is facts about those entities. So for example, we can say that, you know, diabetes is an instance of a disease, right? So what you're essentially doing here is you're constructing a knowledge graph. It's a very structured representation of your data. And there's been a lot of work, for example, the work of Tom Mitchell at CMU, kind of building these knowledge bases. And you can think of them as, again, triplets of entity, relation, entity. And then, you know, using that information to be able to, you know, answer the questions, for example. And this is traditionally what a lot of IT companies are doing as well. Of course, it's a very laborious task. One thing that we'll talk about in this lecture is very difficult to collect the data. You have to manually go in. You have to correct, you know, things that are not labeled correctly, and so forth. So it's a very laborious task to create these knowledge bases. But that's essentially what the big companies are doing, and they're spending millions and millions of dollars to build these very large-scale knowledge bases, right? In fact, the way that Google search works, a lot of it is based on the knowledge base. When you query something, it can understand what is it exactly that you're asking, right? So that's a common thing that's done. However, you know, typically these knowledge bases are incomplete, right? And they can be very noisy. You can imagine, you know, the space of all possible answers or space of all possible entities can be very large. So there's been a lot of work trying to basically do the following. If I give you the question, can I somehow retrieve information in the form of both structured representation, which, let's say, part of the knowledge graph, as well as unstructured representation, which is basically, think of them as Wikipedia articles or news stories that talk about these specific concepts. So that's why sometimes people talk about these data as unstructured data, because it's easy to get unstructured data. I can go on the web and can just query the web. Or I can go and look at, you know, all 50 million passages in Wikipedia articles and figure out what the question is asking and get the relevant concepts, right? And then there is a notion of what's called graph convolutional neural networks, so graph comprehension, where you take the information both from structured data and unstructured data and get the answer. Right? So this is one specific representation when we're actually using some prior knowledge in the form of knowledge bases to help us be able build representations that are much better in terms of being able to answer complex questions. So that's one form of incorporating domain knowledge. And the way you can think about, incorporating the domain knowledge is that, let's say I ask you the question, who voiced the dog in Family Guy? And Family Guy is a show, it's a cartoon show. Perhaps I can retrieve sentences that talk about Family Guy, like you're seeing here on the right-hand side. And then there is also some knowledge graph, some structured representation that tells me about who plays and who voices whom and such. And then the question is, can I share information between these two different sources of data? And how can I do that? Okay. So one way you can do this is, you basically try to link together the knowledge base through the representation of these sentences or, representations that you get from Wikipedia articles. And then based on that, you can find the path to get the answer. So it's almost like what you're essentially doing is you augmenting your knowledge graph with textual information. And that's very important because, as I mentioned before, knowledge graphs are incomplete. They're very expensive to build, whereas the textual information of unstructured text, there's a lot of it on the web. And so that can really help you be able to build systems that leverage both of these sources of data. Okay. And so how do we actually do that? Well, the idea here is that if I have a question, I can get some representation of the question. And typically, we're going to be using recurrent networks, or later on, we'll talk about transformer architectures. Think of them as deep learning models that get the representation of a sequence, sequential representation. So for example, here, we're looking at a question. And we also have what's called entities in our knowledge graph, as well as entities in the textual data. And we typically get that representation using graph neural networks. And then what we do is we're essentially combining text mentions and the entities. And that goes through what's called a graph convolutional neural network to aggregate information across entities in the knowledge graph, as well as representation that's coming from the language. So here, let me spend a little bit more time and tell you exactly how this is done. So one of the big area of research, I think, that we also see in the deep learning community is understanding the graphs and reading the information from the graphs. So let's say I give you a graph with vertices and edges and some natural language question Q, right, which contains a sequence of words. And your goal is to learn a function f such that the output of this function is 1 if and only if it answers the question Q, right? So in a nutshell, we're going to be, building a probabilistic model where the probability of answering correctly the question, given the graph and given the question, is going to be given by this simple softmax expression, right? So H sub Q is the representation that we get from the question, and H sub V is the representation that we get from our knowledge graph, right? And so again, HV is the representation that we get from the knowledge graph by using graph convolutional network. And HQ here is the representation that we're going to be getting from LSTM, which is a type of recurrent neural network. But one thing that I wanted to highlight is that, fairly recently, we're beginning to see a lot of work in the space of using graph convolutions. And if we think about graph convolutions, they're fairly simplistic models, but they actually become very powerful. There's also a lot of theoretical work in trying to understand the representation power of these models. So here the idea is that intuitively, it's actually fairly simple. You're basically saying, well, if I want to update my red node here, and that's my hidden state, think of it as maybe representing some node in your graph. What you do is you aggregate information from the neighborhoods. So you take all the neighboring graphs, and that information flows into your hidden state representation. And then given that representation, that information flows through, other nodes in the graph, right? So conceptually, it's a very simple idea. It's essentially basically uses the graph neighborhood structure to propagate information in the graph, right? And you repeat it for, t number of steps, and that's essentially what's been called sometimes as a graph neural networks, or GNNs. They can be fairly powerful because this function f is a nonlinear function. So you're basically capturing some nonlinear relationship between the information that's coming from the neighboring nodes into the representation of your hidden state at time t. So, in sort of, if you look at it at the high level, essentially you're just using the structure of your graph to propagate information, which is very intuitive. One other thing is there's been extension of using what's called relational graph convolutional networks. So you can have graphs with different edge types. And that becomes very important because edges in these knowledge graphs typically represent relations. For example, one relation could be it's a capital of, so one city is a capital of the country. So capital of would represent a particular relation. And you can parameterize these relations through these matrices, right? And so now when you're collecting information, depending what relationship you're looking at, you're going to be using different parameters for different relations. And so there's a very clean extension to graphs that actually have different types of edge information, okay? And so here the idea is, again, we can propagate information. So given some documents, we can get the representation of those documents. And that information then can flow and get a better representation at of the nodes. And the other way around, like if we have some representation of entities in our graphs, then that information can propagate, and we update the representation that we typically get from our recurrent neural networks. So we can think of information flowing both ways, right? And that's very relevant because, again, if you're trying to answer the question and the knowledge graph doesn't have the information about that specific entity or that specific mention, then you will be relying just on unstructured text to answer the question. So for example, one example I can give you is that, if you build a knowledge graph up until last year, and somebody's asking you something about COVID-19, if you don't have that information in your knowledge graph, right, then you have to rely on unstructured data. You have to rely on news articles and so forth to be able to understand what the question is asking and extract the relevant information. Okay. And in general, what ends up happening is if you just use the textual representation, that's what you essentially have here. Right, so this is without using any prior knowledge or without using any structured data. That's kind of the accuracy that you can get. But if you actually use graph neural networks, right, and you kind of combine the knowledge base with textual information, you can get much better results. And the knowledge base completeness essentially is telling you how complete your knowledge base is. So when we say 50% completeness, that basically says that 50% of the questions would ask you questions about certain facts or mentions that you don't see in your knowledge base, right? So you really have to rely on the textual information to answer those questions. Are there any questions? I sort of, that's one aspect that, I want to highlight is this notion of using deep learning models with graph-based representation. I think there is one question that maybe I can answer. Yes, so the way that we're combining the information from knowledge base and text, let me just, sorry, the question is, how do we actually combine the information from textual representation and the knowledge base? So for example, here's one representation. So the way that we get the HD, which is the representation that's coming from the sentence, is we just basically get the representation for a specific sentence, specific word at time t-1, as well as the representation of that we get from the same entity in your knowledge graph. So for example, if I look at this sentence, I have an embedding of the word McGriffin, right? And that's going to be the embedding, contextual embedding that's coming from my recurrent neural network, for example, right? So if you use bidirectional RNN, you will get some representation of what that term means. At the same time, based on my knowledge base and based on the information of the graph itself, I'll get some representation here as well. And that's this representation. So now when I try to get the new updated representation of, Meg Griffin here, I'm actually combining, in this case, I'm concatenating both of those representations, right? And so now my LSTM state is now kind of contains two things. It contains information that's coming from recurrent network. It also contains information that's coming from the knowledge graph, right? There are probably other ways of combining it, but that's one way of just basically concatenating. And we do something similar, when we update the representation of the knowledge graph as well. Okay, so let me spend a little bit of time also on, another topic which is, related to this, but also fairly interesting, is this idea of building representation, what's called multi-hop questions. So imagine that I give you the following setting. Let's say I ask you the question, where is the company which manufactured Vogelbos headquartered, right? And Vogelbos is a specific type of drug that treats diabetes, I believe. So let's say I ask you this question. How do you answer the question like this? Well, in order to answer this question, you actually have to be able to do a little bit of reasoning, right? You have to kind of say, well, which company actually manufactures this specific drug? And once you get the answer, then you can ask the question, well, where's this particular company headquartered? So that's why it's called multi-hop representations, just because you can't answer the question just based on a single, a single sentence or a single passage. So for example, here you're basically retrieving information, you're trying to get the information that basically says that, Vogelbos is a product of Takeda pharmaceutical company, right? And it's Japan's pharmaceutical company. Once you know that it's a Takeda pharmaceutical company, then you can ask, where is it headquartered? And then you can get the representation. It's actually headquartered in Osaka, right? And so that would be your answer. And you can say, okay, that's fine. The real challenge is that nobody tells you the representations, the internal representations of these models. What you get as a training set when you're building these systems, these models, is that I give you the question and I give you the answer. And you have to figure out on your own, is it a multi-hop representation? How do I find these latent variables, these hidden variables, so that I can answer the question correctly, right? And this is where it becomes challenging, and that's the reason why, many cases, if you ask Siri or Google or Cortana a question like this, most of the time it would just basically say, here's what I found on the web, right? And most of the time it wouldn't be able to answer a question like this, precisely because it kind of forces you to find hidden representations to answer those questions. Right, and you have to kind of like get the correct representation. And that's actually is challenging. It's still an unsolved problem. So I'm going to show you one way of doing this, but it actually represents one of the bigger challenges in NLP and sort of deep learning community, just because being able to figure out building these internal representations that you can find these answers is fairly challenging. Now, how do we want to do that? I mean, there is some prior work on this, but in the prior work is typically trying to heuristically identify some intermediate steps, and it's fairly slow. And the question is, can we do it in what's called end-to-end fashion? What that means is that can we build a system in such a way that we can make it fully differentiable, which basically means that we can learn all of our representations, hidden representations, using backpropagation algorithm. Can we do it efficiently? And more importantly, can we do it compositionally? So it's sort of the fact that, we have a specific structure, right? We're trying to figure out the answer to the first question and then to the second question. So can we build something that's compositional? And that's something that a lot of deep learning models suffer from, right? Because we think of them as black box algorithms that given the input, you just produce the output, right? And so in this case, you could just ignore this structure and you could say, well, here's the question, here's the answer. I'm going to push it through some deep learning architecture such as transformer and just see if it finds out what the answer is, right? But typically, the sort of black box approach doesn't really work well, especially when you have these complex questions. here's a system that we've built just to kind of show you. Let's say I tell you which company founded by Steve Jobs was based in Redwood City, right? And just to sort of show you that this is the system that's analyzing in real time 5 million Wikipedia articles, and that's just basically running on a regular machine, right? So it takes a fraction of a second to analyze 5 million Wikipedia articles, and gets you the answer. So just to show you what the answer looks like, obviously Steve Jobs founded multiple companies, right? So that's what the first passage, the retrieved first passage is, and it basically highlights where the model pays attention to and says this is the relevant piece of information. So here it says Jobs was the chairman and CEO and co-founded Apple, and he also was a member of Disney Company, and then he was the CEO of Next, right? And then the second passage that the model retrieves is that the Next is the company that was based in Redwood City, right? So obviously, you can get the information that Next is based in Redwood City, but you have to know that Next is also the company that Steve Jobs co-founded. So if you can get these, you can retrieve both of these pieces of information correctly, then you can answer the question correctly, right? And this is something that, we wanted to do efficiently. We wanted to do in an end-to-end fashion. So we trained the full model. And this is one of the prototypes that works fairly efficiently. So the question is, how do we do that? Let me. By the way, are there any questions? Before I get into the specifics of how this is done. There's one question. Yeah. So let me sort of. Show you kind of like what's the intuition here and what the underlying structure is. The idea here is that we have what's called a follow relationship. So for example, given a set of entities X, we're going to follow relation R to arrive to the new set of entities X, right? So what we're going to do is we're going to say, let's say X is the name of the drug. Let's say R is the manufacturer, so who manufactures the specific drug. And then the second relation is the location, the headquarter location, right? So if we can identify X, R1, and R2, perhaps we can build a system that basically says, have this follow relationship, right? Like, so given X and relation, find all the X's such that this relationship holds, right? So that's a high level idea. It almost feels like a little like a logical rule, right, that you're incorporating into your overall architecture. And so the idea here, just to explain how we construct this, is the following. Let me give you an intuitive explanation. Let's say I have a bunch of entities, and I have a bunch of mentions. So I have, Family Guy. I have Brian, which is a dog in a Family Guy. I have Seth MacFarlane, which is, the person who voices Brian. And so let's say I have lots of entities and I have lots of mentions, right? So again, we talk about number of entities in the order of millions. Number of mentions is on the order of millions, right? So think of them, mentions in this case are just sentences that we extract from Wikipedia. And so how do we do the follow relationship? Well, one thing we can do is we can expand X to co-occurring mentions. So we basically say, well, if X is the Family Guy, we can expand, we can look at all the mentions where this occurs. The second stage where the learning happens, and that's where the major, where all the advances in machine learning and NLP are taking place, is this idea of figuring out what mentions are based on a specific relation, right? So we, which ones actually respect the relation and which ones are not. And here we're going to be looking at the function f that looks at the mentions in the context and looks at the relation and produces the score. And then based on that, we're basically going to be combining the scores for the same entity and just basically saying that we think that's the right answer. Okay. And one of the key ideas here, surprising ideas, is that we can do everything compositionally and we can do it efficiently using inner products. And so how do we do expansion? Well, actually what we can do is we can say, let's say we have a bunch of entities and we're going to construct a matrix, a large scale matrix, sparse matrix, that essentially says where this particular entity occurs, right? So this matrix is pre-computed. It's a just gigantic matrix that basically says, if I look for the family guy, these are all the entities that we're going to see, right? So it's a sparse million by million matrix, right? So it's basically it's just points, to the mentions where this particular entity occurs. So that's fine. Now, how do we do filtering? Well, here's where the tricky part comes in. Given the relationship, we have an embedding of the relationship. And given the mention, or a sentence in this case, we use the transformer architecture. So it's a very specific architecture that's been fairly powerful. It uses attention mechanisms. It uses it's typically pre-trained on a very large scale data sets. So for example, if you're familiar with models like BERT models, essentially that's what we're using here. And then you're just looking at the scores. You're basically saying which mentions are in agreement with your relationship R. And the transform architecture is pre-trained using language modeling, but then the parameters, specific parameters of F and Q can be trained for the task that we're trying to achieve, right? So here where we're trying to basically figure out which relations are in agreement with the mentions, right? So that basically gives us the filtering stage. And we can optimize for these parameters by using backpropagation algorithm. And so now when we're filtering these mentions, we actually use the top K nearest neighbor search. So given, we have the scores for how well a particular relationship is in agreement with a particular sentence or particular mention. And then based on that, we look at the we do top K nearest neighbor search, which essentially just keeping the top most relevant mentions. And then once we have these mentions which respect the particular relationship, then we do element-wise product, all right? And that gives us mentions that satisfy the relationship, right? And then the last step, what we do is we basically take that representation and we bring it back into the mention space, right? So it's almost like, expanding it to the context of given a particular mention, we're expanding it as given a particular entity, we're expanding to the space of mentions, we find the relevant ones, and then we're bringing it back to the space of mentions again. And so here, one step of this entire procedure is that you have this compositionality, you're expanding to co-occurring mentions, you filter out the mentions, and you're combining the scores for the same entity. And what's interesting about this architecture is that this entire architecture here is differentiable. What that means is that we can actually backpropagate through the parameters in this tau representation in order to be able to optimize for our objective, which is being able to answer the questions correctly. And so it's efficient because it's polylog in the number of mentions. It's closed down the composition. So what's important here is that we can construct this compositionality piece, right? Where we get the relation 1, we get the set of mentions, and then we choose the ones that follow relation 2. And so it's internally, it includes explicit bias where we're basically decomposing our representation into these follow relationships. And if we, trying to answer 2-hop question, we can, look at the composition of both of them. And the entire system is differentiable, which basically means we can train it in an end-to-end fashion. So that's, that's sort of a way of incorporating it. And the way, again, you can think about this system is that it's almost like, given a question, we have specialized neural networks. And one of the neural networks, so the transformer architecture, is, does the soft entity linking, which basically figures out what the question is asking, what mentions is it asking, and then the relationships are extracted using these transformer architectures. And so the entire model is almost, the composition of these modular blocks, right? Each block is responsible for identifying specific relations and specific entities, and then each block produces a set of answers, which we then follow into the next block. So this is how we're using domain knowledge. So it's, instead of it being one big black box model, we actually decomposing into the pieces, and we design specific architectures to follow these pieces. And again, the entire system is differentiable, which basically means that we can, given the answer, we can backpropagate through these blocks and learn specific parameters so that they respect that specific architecture that we're designing here. And just very quickly, and I'll look at the questions. These kinds of the representations work much better, particularly, the gap between 2-hop and the 3-hop representation is much higher than compared to the system of, for example, that uses graph neural networks. And so you can see these jumps here, but, so actually being able to answer these questions, we're not perfectly there yet, so we can't answer 100% of those questions, but we can answer, fairly reliably these compositional questions. And in terms of the speed, these models are very efficient because everything is based on these learned nearest sort of learned inner products based search. So let me stop here, and maybe I can answer a couple of questions. Very good question. So one of the questions is, how do we know how many hops the question contains? That's a very good question. Right now, the model assumes that the number of hops is fixed, so we know a priori how many hops we have. But what we did find is that if we build a system with a 2-hop questions, and the question actually is a 1-hop, what the model does is the model basically uses the first hop to answer the question and just propagates the same information to the second hop. So we don't suffer that much from, we basically can just use the system that does 3-hop questions. And if the question only has 1 or 2 hops, then the model learns to just answer the question and propagate that question forward. So we don't suffer from this notion of actually needing. The only thing that we suffer is the speed, right? Because we have to do this over 3, we have to do it over 3 hops as opposed to doing over 1 if we know that the question contains 1 hop. Right. So let me also, yes, so there are a few other questions, let me, perhaps let me take some of those questions at the end of the talk, because I do want to show you a couple of other examples. This is another example of what's the shape of the family of the viruses containing coronavirus, and sort of retrieves relevant information saying, well, coronaviruses are as a family of specific type of coronavirinae type of family, and then that particular family is spherical, right? So you can get the only time you can answer that specific question is if you find the relevant information in 2 different sources of data. And so that brings me to sort of this notion of a big area of research of common sense knowledge, right? So how do we build common sense? How do we do this multi-hop reasoning? But there's also a lot of work on how do we build abstract knowledge into our systems. Like, for example, to give you an example, that we all know that dogs have 4 legs, right? However, in existing systems today, if you take state-of-the-art, deep learning recognition system, if I give you a dog with 6 legs, just if I create a dog with 6 legs, the model would say, yeah, it's a dog, right? Because it has all the other features of dogs. Whether the dog has 4 legs or 6 legs or 3 legs doesn't really matter, because it looks, all the features are dog-like features. Right, so that's actually problematic, and obviously, how can we incorporate that into deep learning models so that they're more reliable is an important question. Now, I also wanted to spend just very quickly talking about reinforcement learning and control, and just show you some examples of where some of these ideas can be applied here as well, and then I promise I'll jump into the questions. So a lot of this work is carried out by multiple students, and one student in particular. So when we think about reinforcement learning, we typically think about learning behaviors. How do we map observations to actions? And it's interesting because now with actions, we can control the environment. Our actions can impact the environment. So when we think about physical intelligence, right, you have an agent. The agent observes the environment, say it observes this image, and then the agent has to take an action. For example, move closer to that particular couch or sofa, or turn left or turn right, as an example. And so when we think about these agents, they need to move around the world physically. Whatever action the agent takes will impact or will affect future observations. So that's why sometimes these are called active environments, right? Depending what actions I take, if I choose to, move this table to the right, the environment will change, right? And it also requires some notion of spatial and semantic understanding of the scene. Imagine that I give you a task of, for example, going to a specific location. So typically what a lot of systems today, the way that they work is that you have an observation, you have some deep neural network that predicts what action you should take. You get the reward, whether it was correct action or incorrect action, and that's being used to update the model parameters. And this is what's sometimes called end-to-end reinforcement learning, right? So you take actions, you receive rewards, rewards serve as a signal for updating your neural network, and you're essentially trying to update the parameters of the neural network such that you receive more and more positive rewards, and you don't receive more and more negative rewards, right? And so when we think about a task of, for example, one specific application of this is a goal-conditioned navigation. So imagine that I show you an image and I tell you, go find me this image. And you have to move around the house to find a TV. Or maybe I can give you a language instruction, right? Find me the white sofa in the house, right? And so I have to go and figure out where the white sofa is. So I have to understand what's white and what's sofa to be able to execute on this, right? And so in particular, language is, convenient for humans to specify, and it has compositionality aspect of it. So there's a lot of research done in the space of combining language understanding with sort of these idea of reinforcement learning or agents acting physically in the world. Now, when we think about a lot of work in reinforcement learning, it requires exploration, it requires exploring the environment efficiently. And that's one of the big areas of research, in the context of visual navigation, for example. You have an agent that moves around in your house. The question is, how do you efficiently move around in your house so that you can learn about the world you're in as efficiently as possible, right? So that's the notion of exploration. And so when we think about end-to-end reinforcement learning, these black box reinforcement learning algorithms, it suffers from generalization abilities. It's very simple and efficient. So in fact, a lot of progress that we've seen recently in end-to-end reinforcement learning, you've probably heard about, environments like Dota environment where, OpenAI's environment where they can play these complex games fairly efficiently, but they require, 250 years of training, right? Which would not be feasible for realistic robots. And so, the question is, can we actually build something modular and hierarchical, and at the same time incorporating the strengths of learning? So here's the system that we've built. It moves around. It predicts where the closed objects are. So it predicts where the free space is, so that it can move around. It predicts where the obstacles are. And it's a combination of multiple things. Let me kind of just quickly show you what these things are, just to show you the compositionality of the model. So let's say we have some input, which is the visual input. We have something that's called neural slam, which basically creates a map of the environment, local map of the environment of where you are. Based on that, there's something that's called a global policy, which specifies a long-term goal. So for example, it can specify, go to this particular location, or try to achieve some long-term goal. And given that, you have a planner, and a planner, what it does is it plans the path in this partially observed environment. Given that I can plan, I can then create a short-term goal. How do I reach the next, how do I move, for example, 1 meter to the right? And then there is a local policy, which is an instance of reinforcement learning that actually takes this local goal and executes and takes an action. right? And so this is sort of a setting where you have multiple building blocks, much like what we've seen in the question answering system, where you have these local boxes. All of these local boxes are differentiable, so you can actually learn model more or less in the end-to-end fashion. But it has this notion of compositionality. It builds the map of the environment. It understands what the environment is. It tries to set up a long-term goal of where it should go so that it can explore efficiently. It plans how I can reach that goal. And then there's a local policy that actually takes all the local information and then creates an action. Right? And that's exactly what's happening with these models. So the blue dot is the long-term goal. It's basically telling me, you know what, try to reach that goal. And the local goal is, you know, trying to move and avoid obstacles as you're kind of moving around. And so one thing that I want to highlight here is that if you look at traditional reinforcement learning algorithms, you know, trying to look at harder problems where you have to move very far in your environment, traditional reinforcement learning algorithms just basically fail, and they fail very badly. Just because it's very hard for them to learn in an end-to-end fashion, given limited amount of time you can spend on it. Whereas these hierarchical models are actually doing much, much better. And of course, it's not surprising. I think many of you are in statistics. You know, building hierarchical models and modular models has been around for a very long time. I guess about 5, 6, 7 years ago, with the deep learning taking over the world, a lot of work's been done in this kind of end-to-end and black box learning fashion. But for some of these problems, it's actually quite difficult to just use end-to-end, black box neural networks. You actually have to provide, a specific structure or specific environment or a specific way you're learning about the environment, right? The other thing, just very quickly, I wanted to highlight is this notion of using semantic price, a common sense knowledge. Let's say I give you this particular target image and I ask you to find me this image in the environment. And the question is, would you take path 1, path 2, or path 3, right? And so obviously in this setting, you would take path 2, right? Maybe path 1, but you wouldn't take path number 3. And the reason why you wouldn't do it is because you would start reasoning that, stoves are located on the first floor. Like kitchens are typically on the first floor. Very rarely you see kitchens on the second floor in an environment like this, right? And so it's one of those things that can you learn these priors or these representations, or how do you incorporate them into your learning architecture so that you can, you can do it more efficiently. And there's also this notion of building topological maps, right? We've talked about using navigation, but then the question is, can we actually learn something more meaningful? And we can think about, again, graph-based representation of these topological maps, where we have the agent, which is agent's current nodes would represent areas. And in this case, regular nodes would represent explored areas. And then we have what's called ghost nodes, which are representing unexplored areas. And we're trying to reach a particular goal. And then the, I guess in this case, the relationship between relationship between nodes would just be relative positions, or relative positions of these two nodes. So that's something that can tell us something about spatial relationship between nodes. So much like what we've seen in the previous part of the talk, here we've been trying to look at the topological or graph-based representation. And you can think of it as, in the previous setting, we have now graph-based, which updates the topological map. And then the rest of the environment is very similar to what we had before. So the question is, do we go with the graph-based representation, or do we go with some form of, metric-based or neural slam-based representation? Right, so there's two alternative things of doing things, and graph-based representation has its own advantages. And so this is what the architecture looks like. Let's say at time t, you basically look around and you construct a graph with the probabilities that basically tell us, where we should go. So open areas would be higher probabilities, or higher probabilities of finding the goal image that you need to go to. And then at time, you execute it at a certain number, at time t, you create a new representation of the map and so forth up until you hit the target, right? And so here's what this representation looks like. You're constructing these graphs on the fly, and then based on which goal image you need to reach, you basically using that to get to your goal image. Just looking at time. Oh, here's another representation. So this one is actually interesting because here we need to find, I guess, a living room. And so what the model does is it actually, as it explores, it basically figures out that it needs to keep going straight. It doesn't need to look and go into the bedrooms because it's looking for the living room, right? So as soon as it sees the bedroom on the left-hand side, it doesn't need to go there. It goes, it chooses to go forward. So this is where the semantics of it comes in, because if I want to reach a particular target, I can use that information in order to build a better policy, right? And these models, again, when we compare end-to-end learning versus, using topological maps, we can actually do much better. And so it's sort of using graph-based representation in this case helps us, do target navigation more efficiently. Again, here at the high level, I just want to emphasize that we're using these representations, whether it's a graph-based representation or whether it's a modular hierarchical-based representation. And so it's important to figure out what your prior is and what the prior domain knowledge you're using in order to be able to solve these problems, right? And they're also much more robust to noise. So if you have a noise in your estimates, they do tend to work much better. And the last part I also want to say is there's a grand vision of actually building systems that can understand semantically the world around you. Because ultimately, if you want to have a robot that moves around in your house, it needs to have this 3D representation of the world, and it needs to understand what and where things are. So here is a small example. This is actually a physical robot that's moving around in my student's apartment, and he gave me the permission to show it. And the goal is to find potted plants. It's a language type instruction. And as you see that as the agent moves around, it finds the potted plant. But as it moves around, it also builds the semantic map of the environment, right? It sort of builds and understands where the TVs are, where the tables are, where the sofas are. So it sort of builds the semantic representation of the world, so that the next time I ask it to find potted plant, it will go and find it, right? And so this is actually not in the simulation. This is a physical robot moving in the physical world, right? With these policies that we've built. And so obviously there is also a lot of research in going from simulation to real. In fact, the robot that I've shown you was trained in a virtual environment. And then the algorithm was transferred, the execution policy was transferred into the real world, and it's doing pretty well. But obviously there is a lot of research in, how do we bring the physical domain gap, because in the virtual world, the way that we move in the virtual world is not the same way we move in the physical world. There's a visual gap because visually things are different. So there's a lot of work trying to kind of build models that work really well in the simulator, but they're also transferable to the real world. So that's one of the big questions. And obviously there is, when we think about actuation noise, when we think about sensor noise, it goes a little bit more into robotics aspect of things. But this is what the robot actually looks like, right? The physical robot looks like. And so building these statistical machine learning systems that can, for example, do image translation, that can detect in the visual world, images look slightly different than in the real world. How can I, correct for that? Or the other work that we've been doing is looking at the actuation noise, the way that the dynamics, the transition dynamics work in the virtual world is very different from the dynamics in the real world, right? The way that the robot actually transitions from one state to the next state. So there's a lot of work in sort of domain adaptation and bridging this gap between simulation and real. And just to show you, this is the actual, again, this is the physical robot. this is what this robot looks like. It's like a little, robot with, a few sensors, and it's sort of, for some reason, I apologize, my videos are not playing of the real robot, but this is what it looks like, and as it moves around the environment, this is what it's seeing. So let me, I have 5 minutes left, so hopefully my PowerPoint hasn't crashed, but ultimately, building these intelligent agents, I think it's a very exciting times, just because we are now at the stage where we can have these robots that actually move around, that we can train in a simulation, that can actually do interesting things in the real world. They can move around autonomously, they can localize, they can plan, they can perceive language. So the language interface becomes very important, recognize objects around us, and ultimately, building more intelligent machines is the holy grail, as I've mentioned, of building AI agents. So we're now at the stage where a lot of pieces come together, because we have a lot of advances in language understanding, we have a lot of advances in visual understanding, we have a lot of advances in sort of robotics and being able to build robots that actually do move around physically around the world. So it's a very exciting times to combine all of these different statistical ML models and deep learning models into one sort of almost like how do I call it, a master algorithm that can understand and combine these different sources of data and act more intelligently. So on that note, I'd like to stop and thank all of my students. A lot of this work that was done by all of these students working in all aspects of language, machine learning, deep learning, theoretical understandings of reinforcement learning, and so forth. So let me stop here, and I think I have a little bit of time to answer some questions. So I don't know what's the best way to do it.
I think probably Jordan can summarize for us.
Yeah, maybe like if there are specific questions, then people can ask me. Just unmute and ask me. I think that would be.
Actually, the viewers don't have the ability to unmute, so it's just.
Oh, they don't have the ability to unmute. I apologize. So let me start from. So this one we've answered. Would it be faster if your query search isn't a JSON and a look at XR2 and understand where to know R2 to find R1? I think that this one is. Question, would an ad hoc search be better than hopping if you assume initial underlying structure? So the question is, if you're assuming an underlying structure. So I don't quite understand the question precisely. I think that you can, so the way that we're doing right now is if somebody tells us what the first relationship is and what the second relationship is, then things would be easier. Right now, what we do is we're using transformers and we computing parameters and adjusting parameters in such a way that the model essentially tries to pay attention to R1 and R2 because we don't know what R1 and R2 is, right? Perhaps there is a better way of doing this where you can actually build a separate model that tries to identify what's the first relation, what's the second relation, and then based on that, you pass it into the architecture that I discussed. Right now, we're basically just using transformer and just basically say whatever it extracts, and we believe it should be R1. We don't know, maybe it's doing something else. But whatever the output of the first transformer goes into as an input to the second transformer. That's essentially what we're doing. And the first transformer is also trained with a single hop questions, right? So these, when we think about R1 and R2 will have different parameters in these language models. So can the robot recognize a mirror? Ooh, that's a difficult one. We haven't experimented with this just because there's reflection and that creates a lot of problems for the visual understanding of the world. So probably not. I think that right now we're struggling with even things like, laptops located on top of the tables because we need to figure out where the table is physically and the 3D representation of it and understand, where the laptops are and so forth. So there's a lot of work kind of that needs to be done in that space. So we're just at the very beginning of that. Can you comment on the dog flight simulation between the iGen and the human pilot? So yeah, I've heard about this particular setting. I think it's interesting, and I believe that the dog flight simulator was an end-to-end reinforcement learning setting. So as I mentioned before, I think that when we look at the simulators, we can sim the heck out of the simulators. And given your model is big enough and you simulate, many years of simulation, I believe that these models, the black box models, would work well. And they do show that they work well. The issue is that if you actually take this model and you put it in the real world, the question is, how well will it work? The other question is, when it fails, it's very hard to understand why it fails, right? So in many cases, to give you an example, nobody's using end-to-end learning for self-driving cars, right? Because you can't build a reinforcement learning agent that basically says, here are your controls, drive. Well, if you get in an accident, the question is like, why did you get into the accident? And your black box neural network will say, well, I have no idea. I have these billion parameters in my model, and that's the action that I took. Whereas if you look at these modular systems, right, what they do is that when they fail, you can inspect them. For example, they fail because they failed to build the correct map of the environment, right? They fail because, the model predicts there's an empty space, but there's actually a wall. And that's why I bumped into the wall, right? So maybe I should, get a better representation of my walls. Or maybe I got everything correctly and my plan didn't work because I planned to move in this direction, but somehow my plan didn't do the right thing. Or maybe I did everything correctly and I failed to achieve the goal because my local plan just failed. I couldn't execute my, because of my pose estimation was wrong, right? So that's kind of like the high level idea. I don't know how much time I have. I guess maybe I can take one more question. Incorporating the real world, what happens if several unknown objects are introduced into the environment? That's also a very good question. What if you have new objects in your environment? What do you do in this case? Just very quickly, there is a lot of research happening in the space of what's called one-shot learning or few-shot learning. And again, that's kind of a holy grail of computer vision. Because right now, if I want to learn about dogs, I have to give you thousands of images of dogs before the neural network says, I now understand what the dog is. Whereas in this environment, we've been looking at the setting where, we can maybe perhaps identify there is a new object. We don't know what it is. But with kind of active exploration in the real world, what you can do is you can move around this object. You can look at the object from different viewpoints. Perhaps you can interact with an object. And that comes closer to the way that humans learn, right? Like the way that kids learn is that whenever you see a new object, you interact with this object. You can look at the object from different viewpoints. You can grab the object, you can manipulate the object, and then you understand what the object is. I don't know, the first time you see Chewbacca in your room, what do you do? Well, I don't know what this is, right? It's not in my vocabulary. I don't know what this is. It looks like a bear. Perhaps you can look at it from different viewpoints. You can interact with it. And then the human tells you that's what's called Chewbacca. And this, based on this one example, a single label, you actually get so much more information about this particular object. And in this case, I believe that deep learning algorithms should be able to do much better. And so that's where the notion of self-supervised learning comes in. And again, this is something that we're trying to do where, we get so much more information of the robot being able to move around and manipulate the object. So based on a single labeled example, we can collect so much more data, right? And that should help us. Maybe we just need one more example of Chewbacca, perhaps of a different color, right? And then based on that, that's it. We know what the object is, and we should be able to classify it 100% next time we see it. Again, that's kind of a holy grail of building the system, because that's something that we can't do right now in the computer vision, because in the computer vision domain, somebody gives us static images of Chewbacca. Well, if you have a single image of a Chewbacca, what can you do? There's very little you can do with it. right? So hopefully this idea of building intelligent agents in an active sense will help us to start bridging this gap between being, between sort of collecting millions and millions of examples versus agents learning about the environment and learning about objects in a self-supervised way, right? By interacting with those objects, by looking at these objects from different viewpoints. And that's something that we're trying to actively do right now.
Great.
Okay.
Well, we're about out of time. So thanks, Russ, for joining us today and for giving a very impressive talk and providing lots of intuition for how these methods work. Thanks to all our viewers for joining us as well. This was the last lecture of this seminar series, but we would still appreciate any feedback you have about how we could improve this online seminar format in the future. On the distinguished seminar page on the Purdue Statistics website, there's a link where you can share your suggestions with us. I hope we all learned something about deep learning from this year's Distinguished Theme Seminar Series. The series will start again next fall on another timely and important research topic.
Awesome. Well, thank you.
Ross, really appreciate it. Wonderful. Great talk.
Thank you so much.
Beautiful. All right. Thank you very much.
Thank you. Bye.